Hello, this is Math Coach Jenny Gardner, and I'm an academic coach here at SNHU. Welcome to this guide on hypothesis testing for means. Today we are going to talk about the definition, plus the null and alternate hypotheses, finding the test statistic and p-value, and using them to make conclusions. Have to always start with definitions. So let's think, what is a hypothesis test? Pause for a second, and I'm going to ask you to do that many times. Pause for a second and think about what you think a hypothesis test is. If we're going by a definition, it says it's a calculation to determine if a statistic has changed in some way, and we use a statistical level of significance, also called alpha, to decide. But what does that mean? It means that out there in the world, there's a lot of information that we know about different values, different parameters. Like we know that the human temperature on average is 98.6 degrees, 98.7 some people say, and that's the average temperature. But it's not everyone's temperature, so sometimes someone will come along and propose a new situation and say, I think that it's bigger than 98.7, or I think it's less than 98.7. But we can't just take their word for it. We have to test it. And that's what hypothesis testing does. It says, is it this previous amount? Or is it new in some way? Has it changed? Has it gotten bigger? Has it decreased? Is it just different? We're not sure if it's gotten bigger or smaller. We just want to prove that it's different so we can get more research into it. Hypothesis testing is a standard way for us to check to see if it's changed. And that way it can be repeated, this testing, over and over until we're sure it's truly changed. But we want to start with just having some evidence of that change. And that's why we run a hypothesis test. Today we're going to talk about testing means, one sample means. And there are two ways to do this. And in order to do it, we have to decide which one we're going to use. So there are z-test statistics and there are t-test statistics. One is using the normal distribution, that's the z, the normal. And one is using a t-distribution, which is the t-distribution. It's just like the normal, but it is a bit different in terms of the spread. So we have the z-test statistic z0 or the t-test statistic t0. And what you need to decide when you're running a test is which one you're going to use. Some of this could be guided in your textbook, or it might be a project and you need to figure it out for yourself. And so you really want to study those definitions. A lot of it has to do with the population and what we know about it. Do we know the standard deviation? Do we not know the standard deviation of the population? These things help you determine it. So go really study those definitions in order to understand the difference between the two. But I will show you how to find both test statistics, Z or T, and then change them into their p-value. Before we can do any testing, we have to make a null and an alternate. The null is represented by H naught, H0. And the alternate is represented either by H1, H sub 1, or H sub A. So the A would go down the bottom just like the 0 does. So null or alternate. We're not done yet, that's just the beginning. It will have to be defined in every single problem. But the null represents the H0, H sub 0, is going to represent the original thought, what we already know. I call it the baseline. It is our baseline for what we're testing. And then in the alternate, it's our proposal of what has changed. Has it decreased, increased, or just changed? So if we think it's decreased, we use the first symbol, less than. If we think it's increased, we use greater than. And if we think it's just changed in some way, that there's a difference, then we would use the equal sign with a line drawn in it. The less than represents the left tail. So if we have that distribution of a symmetric distribution, either T or Z, and we were trying to figure out less than, it would be this area over here, and that would be less than. If we're trying to figure out greater than, it would just be the area on the right. And if we're trying to figure out one or the other, that's the equal sign with the line through it, and that's two-tail. So left is less, you see how it's drawn on the left. Right is greater than on the right-hand side, and two-tail is both, which is the not equal to, and it could be either one. So for every problem, you first define your null and your alternate, then you look at your alternate and say, which symbol did I use? Because that's going to tell you left, right, or two-tail. And then we calculate with the test statistic and the p-value. And finally, our p-value and our test statistic are going to tell us a conclusion based on some level of significance. Now, the level of significance tells us how confident we are in our results, how much we think it's changed, how significant our results are. So if I am 95% confident in my results, in my understanding of where the mean is and my calculations, then I would have a leftover bit of 5%. So if I'm 95% confident, what's left over is 5%, also known as 0.05. This one comes up a lot. It's very common to see this. This is our level of significance alpha if we're 95% confident. There are other numbers that might come up. I'm going to use 95% as my confidence and therefore 0.05 as my level of significance. So this is going to help me form a conclusion. We'll do that with some real numbers. And when we're doing that, let me just erase this for you. After we get a conclusion, we'll be able to answer whatever research question we were wondering about. So remember, define the null and alternate, determine if it's a left tail, right tail, or two-tail test, find the test statistic and the p-value, and from that, form a conclusion and answer your questions. So we have a scenario here. So let's try this out. We get to do this process. All right, so we're going to start with defining our null and alternate. And this is a time I'm going to say pause for a moment. Go back for a second if you need to, and try to create the null and alternate for this particular scenario. Let's say the average gaming time in the USA for 18 to 25-year-olds is approximately 2 hours per session. And the distribution of the population is considered approximately normal. A local club thinks that it's increased since that statistic, that parameter was determined. So they think it's increased from the 2 hours per session. And they decide to take a random sample of 20 to see if their area, where they live, is higher than this average. So in the null, we have the baseline, and the baseline said that the average video gaming time is 2 hours per session. And the alternate says that they think it's gotten bigger, greater than 2 since then. So greater than 2, they think that it's more than 2, over here somewhere, bigger than 2. So that would be a right tail test. We're going to find the test statistic and the p-value with a calculation, with a formula for test statistic and a calculation for p-value in Excel. And I will have a visual example too of p-value and the relationship. And then we'll form a conclusion based on the level of significance of 0.05. And just to clarify what question we're answering, we want to know, is there evidence to suggest that the gaming time is higher to suggest an increase. So we need to know if there's any evidence, and our test statistic and p-value are going to be our evidence. So it's important that we determine those. Okay, so now here we are in Excel, and I have collected the data of 20. Apparently I only did 15. Hold on, let's do 20. Okay, so we have 20 numbers here, all 20. And this is what we said. We said our null and alternate right here, that the mean was equal to 2 or the mean was greater than 2. Those are our options, this one being the null and this one being the alternate. And now this is the formula for test statistic. It says x bar minus the mean divided by the standard deviation over the square root of the sample size. That is our formula. So we need to find those things. We need the mean, we need the standard deviation, we need the sample size in order for this to work. So what I'm going to do is I'm going to do a descriptive statistics analysis in the data analysis. And if you don't know how to do this, I would go back to the descriptive statistics video that you'll find linked in our video description. So I'm going to go here to data analysis. I'm going to do descriptive statistics, input range here. Just click and drag to select that. And I'm going to get my summary statistics. But I want it to go right here. So my output range, I'm just going to click this box. And I accidentally deleted this, so we're just going to do it again. You get to see me highlight it all again. Okay. So this is the information that's going to be analyzed, and this is where it's going to go. And I want summary statistics, and okay. Good. So this information is what we calculated for our data. This is our sample statistics. All right, so now we get to use this information. This mean is our sample mean, so this is x bar. We need that. This is our standard deviation. We need that. And all the way down here at count, that's our sample size of 20. We had 20 pieces of information. So now I can do the formula. Equals the sample mean. And it says minus that u symbol, that mu. And I up here said that it was 2 originally. So the population mean is considered 2 because that's the one that is in my hypothesis. I'm going to put parentheses around these. And just to be clear, x bar minus the population mean. X bar population mean. Divided by the standard deviation over the square root, SQRT, it comes up right here, SQRT, and then we have to put it in, N, 20. I also like to put the bottom in parentheses so it knows to calculate that separately from the top. So if you look here, just to reiterate what's here, x bar minus the population mean divided by standard deviation over the square root of n. That is how we calculate test statistic. And I'm going to hit enter. And that's going to be the same down here for my t and my z. So this is going to remain the same. I'm just copying it in. So that's the same. The difference comes in the p-value. That's going to be different. And so when we're calculating test statistic, we're using the same formula for both. And I'm just going to open it up one more time, and you can go back again, but just look at this and look at what I used to calculate, okay? This is the formula. I just reiterated it here. All right, so now we're going to find the p-value for our z test statistic, and we're going to find the p-value for our t test statistic, because that's what's going to be different, because the z and t use different distributions. So for the t, let's start there. I'm going to write equals t dot dist. And we have three options. We have the regular one that just says t dot dist. That's for a left-tailed test. We have one that says 2t. That's for a two-tailed test. And we have the one that says RT for a right-tailed test. And that's what I want because I'm using greater than. So now that I have that, all I need to do, I double-clicked on it, and it says t.dist.rt, and I'm going to now select my test statistic. And then it says degrees of freedom. Well, degrees of freedom is just your sample size. In this case, your sample size minus 1. So we're going to say our degrees of freedom is 19. So we have our test statistic, and we've got our 19 because it's one less than our 20. And I'm going to hit enter. And this is my lovely p-value, but it has an e in it, and that's a little confusing to some people. So I want to show you, you change that by going number and then this button until you start seeing your numbers. So that is our p-value. It was on a scientific number and we just want a regular number so we can see what the real number is. And so our number is 0.00000465. So that's our p-value. Now for our z test statistic, we don't use the t distribution. So it's not going to say t.dist. It's going to say norm.dist. We want the standard normal distribution. So we want norm.s.dist. And then we'll select our z statistic. And we're going to type true. We need true in order to find our p-value. But that's for left-tailed. To get right-tailed, we're going to say 1 minus this. If you were doing left-tailed, you leave it like it is. If you're doing right-tailed, you're going to want to do 1 minus. So we're going to do 1 minus this number. Now we have 1 minus the normal standard distribution with our test statistic and the word true. So it's a cumulative so that it gets us p-value. And I'm going to hit enter. And again, that E popped up. It really likes to do that. So we're going to change it to number. And we're going to click this over until we see something. And now we have our values. So we have our test statistic and our p-value for z, and our test statistic and our p-value for t. T like taco, z like zebra. Zebra, taco. Okay, that's how to do it in Excel, and we're able to get those numbers, and we'll interpret them in just a second. But look at this cool visual thing that I want to show you so that you understand. And this is utilizing a program called StatKey from lock5stat.com. And I want us to look at the normal distribution versus the t distribution and just kind of see what happens. It draws it much better than me, first of all. I mentioned technology does this better. If we look at this, it asks us, well, what's our mean and what's our standard deviation? Well, in actuality, we want to look at not changing those. You don't need to change those. We can leave those alone. We're going to look at just up here clicking right tail. Down here is where we will put in our test statistic. Now, if our test statistic was 1.96, our p-value would be up here at 0.025, but that's not what we got. So let's go look. Our test statistic, and we're just going to copy it, is this 4.9299677712 number. And when I put it in here, I just clicked on the number and it let me type it in. Now I have, like Excel told me, this tiny little number with an E. And that means that this is a really, really small p-value. But what I like about this drawing is that it shows you and helps you understand what p-value is. This number test statistic is the number along the bottom, and then the p-value is what's left over on the side, the area that's colored in, the proportion of this graph that's left over. So if our number was something like 2, we could visually see that the p-value is in red. But as it gets bigger and bigger and bigger, it goes off the charts, off the side, and it gets so small that it ends up being that 0.00000041, something like that, something so small it's no longer on the screen. So when we put that in here, we can see, oh, that's such a small area that it's not even on the chart. And that's what we're looking for in p-values. So we'll talk about that with the conclusions. Let's look at our t as well. For t on this chart, it first asks degrees of freedom, just like it does in Excel. So we said that's 19. We're still doing right tail, and we have our value. But we see that the number not as small. It's still able to show you the whole thing. So it's still over here, but it's not as far over, and the area is a little bit bigger than it was. But they're still both really small numbers because we're seeing something really cool with this. So let's look at what this means. This one's p-value and this one's p-value, both really small numbers. Okay. All right. So we need to know if we're rejecting H0. And so what we're going to do is we are going to look at that distribution again. But, you know, I'm drawing it instead of the program. So we said that our alpha level of significance is 0.05. And that is what we're testing against. And then our p-value, let's do the one for the t distribution, for instance. Let's just go out like 0, 0, 0, 0, dot, dot, dot. Our p-value is on a different chart based on our test statistic, like we saw in that graph. This one over here is based on t star, meaning it's based on a t-score, and it's called critical value. So test statistic on the right, critical value on the left. When we look at this, what we want to know is, does our p-value, this really small number in our case, it's so small that it's 0.0000 before anything else, does that fit in to our significant area? Because this area over here, this 0.05, is signifying significant change. So this is our significant change area, level of significance. And so it's identifying significant change from our question. And so we want to know, well, is ours small enough to fit into that significant change area? And one way we can ask that is to look and see if p-value is less than our alpha number. And so in this case, we're saying, is 0.00000 blah less than 0.05? Well, this number is basically so small that it's very close to 0, and this one is 0.05. Is that smaller? Yes. So yes, it's less, and therefore we can reject the null because it has significant change. So what does that mean? It means that if we reject the null, we are saying we have evidence of a change. So I'm going to pull up our null and alternate again. H0 said that it was still 2 hours of gaming per session. HA said that it was bigger than 2 hours of gaming per session. So if we're rejecting the null, if the p-value is less, and we're rejecting the null, there's evidence that it's gotten bigger. There's evidence to support the alternate. So do we have evidence of an increase in gaming hours? Yes, the p-value was our evidence. But If the p-value was not less, we would not be rejecting and there would be no evidence. So they are exact opposites. So if it was do not reject, because the p-value is greater than alpha, and we would be not rejecting if, that's not what's happening in this case, but if this was happening, then where there would be no evidence of a change, no evidence to support HA. To support that change. So ruminate on that, think about it. Pause it, go back to what we started with, go back and look at our information over here and this scenario, and we can say, is there evidence to suggest a change? Yes, because our p-value was small. Change is indicated when the p-value is lower, is smaller than that significant change area, than that significant 0.05 or whatever number you're using for significance. And therefore, the club was right. They have seen a change, and now we'd have to investigate it further to see if it was truly a change that was occurring or if it was a fluke. And we'd have to do the test over and over again to decide. So congratulations, you conquered hypothesis testing, and thank you so much for watching our guide on hypothesis testing today. Please read Academic Support's video description on this video for further academic support resources, some of which I mentioned during the video. And have a marvelous, marvelous day.